Okay, at the previous lecture we began to construct a measure on a locally compact group. At the end of the lecture I've made some stupid typos. Sorry about that. So today let's start by recording some notation and by fixing the typos. So the result we are going to prove is the existence theorem for our measure, or equivalently, the theorem of the existence theorem for a positive left invariant non-trivial functional on the space of compactly supported continuous functions. So suppose that G is a locally compact group. I claim that there exists a positive linear functional I on the space of continuous compactly supported functions on G, which is left invariant and is not identically zero. I is left invariant and is not identically zero. So we have seen at the previous lecture that the existence of such a functional is equivalent to the existence of a left invariant non-trivial measure, that is, a hard measure on G.
Could you recall what is C of G?
C of G is a space of continuous compactly supported functions on G. Support of F is compact. So by the Rees-Markov-Kaputani theorem, there is a one-to-one correspondence between the positive level measures on G and linear functionals and positive linear functionals on this space. So instead of looking for an invariant measure, we'll try to construct a left invariant linear functional. So technically, this is essentially easier. Maybe this is not that this cannot be visualized like in the case of measures, but this is easier technically. So the first lemma we proved at the previous lecture was rather easy. You have two functions, f and g, continuous functions, positive. So the plus here means that we consider non-negative functions, and g is not zero. Then there exists constant c, and there exist finitely many points in G, such that f is dominated by c times the following sum. So we take finitely many translates of G. And by using this lemma, we introduce the following notation. If we have two such functions f and g, then we defined something like a relative integral of f relative to g to be the infimum of the following set. So we consider all finite sums, ci, from 1 to n, such that f is dominated by the following linear combination of translates of g for some points x1 to xn in G. So lemma 1 implies that this is well defined, that is the set whose infimum we are trying to take is non-empty. And of course Ci are non-negative numbers here.
So the set is non-empty. We take the infimum and call it, let's choose a temporary name, a relative approximate integral. Of f relative to g. And the geometric idea behind this number is as follows. Suppose that g is the real line, and suppose that g, little g, the function little g, is a continuous approximation to a step function of the following form, and u is a suitable neighborhood of the identity. So suppose that this is f, this is the graph of f. So the idea is that if f is nice enough, then the number which appears here, the sum of these numbers ci's, is nothing but the sum of the areas of these rectangles. Assuming that the integral of g is 1. So this looks like something like something which is close to the integral of f. So if the support of g is now, if we take the support of g sufficiently small and f is sufficiently nice, then this number is a reasonable approximation to the integral of f, assuming that the integral of g is 1. And in the general case, this is something like the integral of f divided by the integral of g. So that's the idea behind this number. We proved that, not just proved, but actually observed that this number has the following simple properties, lambda 2. First of all, this relative integral is positive homogeneous. We have the following quality. For negative c, which is quite clear because if we multiply c by a constant, then if we have this inequality, we'll multiply the left and the right hand side by the same constant, we still have the same inequality. So this sum is multiplied by c. And the infimum is also multiplied by c. Second, this number is, this functional is subadditive, has the following subadditivity property. Which is a simple exercise, actually. If we construct such sums first for f1 and then for f2, and add the first sum to the second one, we get a similar linear combination which dominates f1 plus f2. So the relative integral of f1 plus f2 is less than or equal to the sum of the respective sums. And by taking the infimum again, we get this inequality. The third observation is almost immediate, that the relative integral is left invariant. Which is immediate from the construction. Property 4 is that if we have two such functions, so as before we assume that g is not 0, then this is greater than or equal to the supremum norm of f divided by the supremum norm of g. Well, again, to get this inequality, we simply evaluate the left-hand side by the absolute value of the right-hand side. Of course, the supremum norm of the left translates of g. All of them are equal to the supremum norm of g. So the supremum norm is translation invariant, and we get that the supremum norm of f is dominated by the sum times the supremum norm of g, which is exactly this inequality. And the property 5 is that
something like transitivity, you have three functions, f, g, and h, and we have the following inequality. Assuming that h and g are non-zero. This is also a simple exercise, which is almost immediate from the definition. Okay, now if we want to construct our left invariant linear functional, the idea is now to take g and to make the support of g smaller and smaller. The picture shows that in this case we can hope to get something like the integral of f. The problem is that formally, if we do it literally, then the denominator here goes to 0, so the whole number goes to infinity. And to avoid this problem, we must normalize our relative integral by choosing once and for all a fixed function whose integral will be declared to be equal to 1. So we introduce the following notation. We choose a function of 0, a continuous, compactly supported non-negative function, which is not identically 0. So this will be a kind of reference sample, that is, a function whose integral will be declared to be equal to 1. And we define for every function phi, non-negative function phi, which is not identically 0, the map I phi, defined on all non-negative compactly supported functions, by the following formula, I phi of f equals the integral of f relative to phi divided by the integral of f0 relative to phi. In the previous lecture, I exchanged f0 and phi, which is formally this is admissible, but this is not convenient technically. So the good definition of phi looks as follows. Anyway, it's clear that if we substitute f0 here, we get 1. So this number takes f0 to 1. And comparing lemma 2 with the definition of phi, we obtain similar properties of phi, lemma 3. So again, let's choose a temporary name. Let's call it just an approximate integral. An approximate integral of f. So lemma 3 looks as follows. The approximate integral is positive homogeneous. We have this equality for every non-negative number c, which is clear because this number has this property, and the denominator is constant. It doesn't depend on f. For the same reason, I phi is subadditive. The relative integral, or the approximate integral, is subadditive. We have the following inequality. And left invariant. And another useful property, property 4, is that this approximate integral satisfies the following double estimate. So this estimate is always true. And if we assume, moreover, that f is non-zero, then this can be estimated as 1 over the integral of f0 relative to f. So this is true if f is non-zero. Again, there were some typos
typos here at the previous lecture. I apologize about that. So let's check that this is indeed correct. I hope now there are no more typos here. So let's prove part 4. This is more or less clear from property 5 here. Well, indeed, I phi of f is f over phi over f0 over phi, and this is less than or equal to this number. And this is obviously correct because of this. Lemma 2, part 5. And conversely, f over phi over f0 over phi is greater than or equal to 1 over f0 over f. Is that correct? Well, I hope yes. This is f over phi. Now we change the inequality to the opposite one. Yeah, so we multiply by this number and we get the inequality 5 in lemma 2. Okay, again true by property 5 of lemma 2. Okay. The next lemma, and this is one of the key points of the proof, lemma 4. Roughly it states that if the support of phi is small, then I phi is not just subadditive, it is almost additive in the following sense. So suppose we have two functions, f1 and f2, two continuous, non-negative, continuous compactly supported functions. I claim that for every positive epsilon, there is a neighborhood of the identity, neighborhood U of the identity, such that for every continuous compactly supported function phi, which is not identically 0, and such that the support of phi is contained in U, we have the following inequality: I phi of f1 plus I phi of f2 is less than or equal to I phi of f1 plus f2 plus epsilon. So roughly this means that if the support of phi is small, then I phi is almost additive in this sense. The proof is a bit technical. So before proving lemma 4, let's deduce now our result from this lemma. Let's show how this lemma implies the existence of a left invariant positive functional. Proof of theorem. So let's introduce some notation. Let P denote the set of all continuous non-negative compactly supported functions, except 0. Then, for every phi in P, I phi becomes a map from P to positive numbers. Two positive numbers. Moreover, we can say more. Let for every f in P, let SF denote the following interval, equal 1 over f0 over f to f over f0. And let's now look here. We see that I5 of f is between these numbers, so it belongs to SF. The map I5, considered as a map from P to real numbers, to positive numbers, sits in the product of these intervals. So number 3 implies that I5 sits in the product of SF. So let's denote this product just by S. What is important here is that this set is compact. The set is compact because this is the product of compact intervals, closed intervals. So now the idea of the proof is roughly as follows. We want to take something like a limit point of the family I5. If I5 were a sequence, then we know that, and if it were a sequence, and if this compact were retrievable, then we could take a limit point. But we must be careful here because, first of all, this is not a sequence, and there is no natural order relation on this family I5. We can overcome this by using filters instead of sequences. But actually, the easiest approach is to replace limits by intersections of suitable compact sets. So let's introduce one more notation. For every neighborhood of the identity, every neighborhood U of the identity in G, let's consider the following set KU, which is obtained as follows. We consider the functions I phi, where phi runs over P, such that the support of phi is contained in U. And we take the closure of the set in S. So this is a closed subset of S. First of all, observe that this set is non-empty, just by Urson's lemma, because of the existence of such functions with support contained in U. And let's also observe that if U is contained in V, then KU is contained in KV. This is also clear from the construction. Hence, if we take now finitely many sets of this form, say KU1 up to KUn, and take their intersection, then this intersection contains K corresponding to the intersection of the neighborhoods U1 to UN. And we have already observed that this is not empty. This is not empty. So if we now look at the collection of all such sets KU, we have just proved that this family has the finite intersection property, which means that the intersection of finitely many sets of this form is not empty. And now the standard compactness argument implies that the intersection of all sets in this family is not empty. Just because the complements of these sets, if it were empty, then the complements of these sets would form an open cover of S. We could choose a finite subcover, but this contradicts the finite intersection property. So the intersection is not empty. Okay, let's take an element I in this intersection. So this is an element in S, and in particular, this is a function from P to positive numbers.
Sorry, I have a question.
Yeah, sure.
KU is the set of some linear functionals, right?
Not linear, because they are so far they are defined only on non-negative functions.
Oh, okay. But it's the set of functional.
Yeah.
Okay. And you said that it's in S, but S is, for me, is just some product of, like...
Well, S is a subset in here. This is the product of the set of all functions from P to positive numbers can be considered as a set of all families of positive numbers indexed by elements of P. And here we consider those functions which satisfy this estimate. So functions from P to positive numbers are just families of elements, families of positive numbers indexed by P. And the product of SF is also consists of some families such that each AF belongs to SF. So this is just a subset in here.
Okay.
So S also consists of functions. This is a compact subset in the set of all such functions. We simply interpret functions from P to positive numbers as the product of many copies of half lines from 0 to plus infinity.
Okay.
Okay, so now I becomes a function on P, a positive function on P. And let's now show that I claim that I is positive homogeneous, additive, and left invariant. Why is it so? Let's now, first of all, let's write explicitly this condition. So I belongs to the intersection of this family. What does that mean explicitly? This means that for every U, for every neighborhood U of the identity, I belongs to KU. So what is KU? KU is the closure of this set. So I belongs to the closure of this set. This means that for every neighborhood of I, the intersection of this neighborhood with this set is non-empty. And what is a neighborhood of I? Well, the topology on the topology on the set is the product topology. So by definition of the product topology, a typical neighborhood of I is indexed by a positive epsilon, and by finitely many points in here, that is finitely many elements in P. Say F1 to Fn. So for every such elements, we can find an element in this set without closure. That is, we can find phi, where exists phi in P, with the support contained in U, such that I phi belongs to the respective neighborhood of I. That is, which means that I evaluated at every function from our finite family is very close to the I phi evaluated at the same, let's notice phi j, fj, evaluated at the same functions fj. It's less than epsilon whenever j runs from 1 to 2. So this property is immediate from the definition of the product topology on the set of all functions from P to positive numbers. Let's know this property by star. And let's now combine this property with lemma, well, first with lemma 3, where is it? with lemma 3. So I is pointwise close to I phi. So the combination of star with lemma 3 implies that I is positive homogeneous, that is, has property 1 of lemma 3, sub-additive, and left invariant. For a simple reason that it can be approximated pointwise by the functions of the form I phi. Okay.
Positive homogeneous.
Positive homogeneous means this.
Yeah.
Yes, this is positive homogeneous in the sense that we can, well, in the sense that this property holds.
Okay, but let's now look at lemma 2. And let's combine property star with lemma 2. Oh, sorry, lemma 4. This was lemma 4. let's look once again at lemma 4. So if you take two functions, f1 and f2, and approximate pointwise I phi, I with I phi on three functions, f1, f2, and f1 plus f2. You have three functions, the first one, the second one, and the third one. And approximate I by I phi in this sense. We see that I satisfies a similar inequality. Well, probably we have to replace epsilon by 4 epsilon. But this is not essential, because epsilon is arbitrary. So we conclude that I is additive, because epsilon is arbitrary. In the sense that I of f1 plus f2 equals I of f1 plus I of f2 for every f1 and f2 in P. This is almost what we're looking for. The only real problem is that so far I is defined only on positive or non-negative functions. But there is a standard procedure of extending such a function to all compactly subcoded continuous functions. And the procedure is almost the same as in the case of the usual Lebesgue integral. Namely, first of all, we let I of 0 equal 0, which is quite natural. And now for every continuous compactly supported f on G, we can decompose f in the following linear combination: f1 minus f2 plus I times f3 minus f4, where all these functions fk are non-negative. This is the real part, this is the imaginary part, and each of them is decomposed as the difference of two non-negative functions. And we let I of f equal I of f1 minus I of f2 plus little I of f3 minus I of f4. It's a simple exercise to show that this is well defined. So I becomes a well-defined linear map on all continuous compactly supported functions. This is well-defined. Linear and non-trivial. And left invariant. So the proof of this exercise is exactly the same as in the case of the Lebesgue integral. So first Lebesgue integral is constructed on non-negative functions, and then we extend it to all functions by using this procedure. So in this case, the proof is exactly the same. And this completes the proof of our theorem. So this is the functional we are looking for. So now to complete the proof, we have to come back to lemma 4 and to prove lemma 4. Okay, so let's look at statement. So if we try to do this by definition, we must do something like that. We must choose a linear combination of translates of G, which dominates F1 plus F2. And then somehow show that this the same linear combination dominates the left-hand side of this form. But for technical reasons, so the first technical trick here is to replace F1 plus F2 by a slightly bigger function. So let F denote the following function, F1 plus F2 plus an auxiliary function delta U, where delta is a positive number, which will be specified later, and U is a continuous compactly supported function, non-negative continuous compactly supported function, which is identically 1 on the support of F1 plus F2. For example, if G is compact, we can let U equal identically 1. But if G is not compact, then we must choose something like that. Anyway, such a function always exists by Urson's lemma. Why is it better than the sum, just the sum F1 plus F2? It is better because we can divide F1 and F2 by F. We can write Fk in the following form, F times Hk, where Hk is also a non-negative compactly supported continuous function. This is a little exercise in general topology, so we simply let Hk equal Fk over F, where F is non-zero, and 0 where F is 0. So the exercise is to show that it is continuous, but this is a simple general topology. So this explains the role of this extra sum delta U. Okay. Let's now choose a finite linear combination of translates of G, of translates of phi, sorry, we calculate integral relative to phi. So let's choose finite linear combinations, or combination of translates of phi which dominates F. So suppose that F is less than or equal to the following sum, Ci Lxi phi, where Ci are non-negative numbers and Xi are points in G. So now the next idea is to subdivide the sum into two pieces, such that the first piece dominates F1 and the second piece dominates F2. So to do it, we simply multiply this, this inequality by H1 and by H2. We multiply it by H1 and by HK, and we see that Fk is less than or equal to the following sum, Ci Hk Lxi phi. But as explicitly, we have the following inequality: Fk of x is less than or equal to the sum Ci Hk of x phi evaluated at x a inverse x. Well, this is not very promising because this sum is not of the form which appears in our definition of a relative integral. Indeed, Hk of x are not numbers, they are functions. That's the problem. They are not numbers. Now, so the next trick is to use the uniform continuity of the functions h1 and h2. So for every positive epsilon, we can find a neighborhood view of the identity such that for every x and y in G, satisfying the following inequality. X inverse y belongs to U. We have the following inequality: hk of x minus x hk of y is less than epsilon. This is the uniform continuity of our functions h1 and h2. Okay, let's now suppose that the support of phi is contained in U. So if now xi inverse x is not in U, then the right hand side of this inequality is 0. The right hand side of this inequality is 0. Otherwise, if it is in U, then we use this property, and we see that hk of x minus hk of xi is less than, oh, sorry about that. What I want to have here is not epsilon but delta. I mean the same delta which is here. So I remove epsilon from here and require I want U to be chosen in such a way that this is less than delta. So now this will be less than delta, and by looking at this inequality star, we see that fk of x is less than or equal to the following sum: ci hk of xi plus delta times phi evaluated the same point. And this is true for every x in G. This is true if this condition holds, and if this condition, and this is true if this condition holds. So in any case, we have this inequality, and this is good because now these are numbers, and they have the same sum as which appears in the definition of relative integral. So we can now add these two inequalities. So we have this inequality for 1 and 2. We can take the sum. Sorry. 10.
I don't quite get it. There is like if one of xy's is such that I inverse multiplied by x isn't.
If one of them is 0, then the respective summand is 0. So we can consider only those summands for which this is in U. Otherwise, all other summands are 0.
Okay, but there.
We just throw away the summands where this number is where this point is not in U.
Okay.
And for all other, if we look at non-zero summands, if we look at non-zero summands only, we must have this in U.
А это U берется из этой непрерывности равномерной.
Да, совершенно верно. Вот это в точности равномерная непрерывность на функцию h1 h2. Okay, so we take the sum of this expression for 1 and 2, and we
see that f of x is less than or equal to sum of number ci, h1 plus h2. Well, if we look at the definition of f1 of h1 and h2, where is it? I can't find our definition of H1 and H2.
We find them such that fk is f.
Yes, I remember, but I can't find it on the blackboard. That's the problem.
Они направо.
Я просто направо, но где они направо?
Нет, только
Так назад
влево.
надо, да. Еще чуть.
Вот.
Вот оно.
Oh, thank you. Good. So, what I want to observe now is that H1 plus H2 is less than or equal to 1. So, for H1 it's something like F1 over F, and H2 is something like F2 over F. F1 plus F2 over F is less than or equal to 1. So, hk of xi plus h1 of xi plus h2 of xi is less than or equal to 1. So I can replace the sum by 1 plus delta times phi I, phi of xi inverse x. Because h1 plus h2 is less than or equal to 1. Okay, so in other words, I have the following inequality: f is less than or equal to this is correct, but this is useless. Sorry. First of all, we have to evaluate the relative integral. This is correct, but before taking the sum, we must evaluate the integral. This inequality, if we consider it for k, where k equals 1 or 2, we deduce that this implies that the integral of fk relative to phi is less than or equal to the following sum. Plus delta. This is true where k equals 1 and 2. And we can now take the sum. f1 over phi plus f2 over phi is less than or equal to the following sum. And here we replace hk of xi by 1. Because h1 plus h2 is less than or equal to 1. Let's now recall that Ci, let's recall what Ci was. So we have chosen an arbitrary linear combination of translates of phi, which dominates f. So by taking the infimum over all such representations, we deduce that f1 over phi plus f2 over phi is less than or equal to 1 plus delta, and the sum of these numbers ci, the infimum of all such sums, is exactly the relative integral of f over phi. Okay, if you now divide everything by this number, we divide the left-hand side and the right-hand side by this number, we get a similar estimate for the approximate integral I phi of f1 plus I phi of f2 is less than or equal to 1 plus delta times I phi of f. And let's now recall what f is. f is f1 plus f2 plus delta u. Plus delta u. But we know that I phi is subadditive. So by the subadditivity of I phi, we can estimate this as follows: 1 plus delta I phi of f1 plus f2. And it is positive homogeneous, so we can write delta here. Delta I phi of u. This is almost exactly what we want to prove, because this is almost this number. This is equal to this number plus delta times something. But a little problem is that this something also depends on phi. So we must evaluate it by another constant which doesn't depend on phi, but it's quite easy. So the first sum is I phi applied to f1 plus f2 plus the second sum will be delta multiplied by the same number, but we recall that this relative integral, this approximate integral can be estimated as follows. This is special case of our lemma 3. And similarly, the last summoned delta times 1 plus delta times I phi of u. Here we estimate I phi of u as follows: u over f0. And this doesn't depend on phi. This doesn't depend on phi. Delta is small. So clearly, if we choose now delta small enough, this will be less than epsilon. If delta is small enough. And this completes the proof of lemma 4. So we see that if the support of phi is contained in a suitable neighborhood of the identity, the sum of these two integrals is less than or equal to this one plus epsilon. This is exactly lemma 4.
How did we get the last line again?
This one. So we just have 4 summonds here. 1 times this number, and this is here, plus delta times this one. But we know, so let me write this down somewhere here. So we know that I phi of f is less than or equal to f over f0.
Okay. Yeah.
So we have used this inequality here and here. Why is it useful? It is useful because the right-hand side doesn't depend on phi. So we want something small multiplied by a constant. And this is exactly something small multiplied by a constant, and this is also something small multiplied by a constant. Okay. So now we know that left power measure exists. Our next goal is to show that it is essentially unique. That is, it is unique up to a positive multiplicative constant. Uniqueness. Power measure. First of all, we need a couple of technical lemmas.
Извините, а вот мы сказали, что вот если дельта вот, достаточно мало, но при этом мы там по дельте выбирали вот окрестность, которая содержит носитель.
Ну, на самом деле, в учебнике пишут наоборот. На самом деле, правда такая, чтобы сперва довольно странным образом, если бы мы писали учебник, мы бы сказали, вот для данного эпсилон найдем дельту так, чтобы выполнялось вот это. Чтобы это было меньше эпсилон. Но тогда было непонятно, с чего мы вдруг такое, откуда мы это взяли. Вот. А потом уже по этому дельте, сперва по эпсилону нашли дельту так, чтобы выполнялось вот это, а потом по дельте нашли окрестности. То есть никакого жульничества на самом деле. The point is that we couldn't guess from the very beginning that delta must be chosen in this way. But clearly such a delta exists. If delta goes to 0, then this number goes to 0. So if delta is small enough, then it is less than epsilon. So first we give an epsilon, we choose delta satisfying this estimate, such that this is less than epsilon. And then we choose U, the neighborhood of the identity U, by using this delta and by using the uniform continuity of our functions. That's the idea. Okay, so before we prove the uniqueness, let's prove two simple lemmas. Lemma 1. Suppose the G is a locally compact group. And mu is our measure on G. Then, first of all, I claim that the measure of every non-empty open set is strictly positive. For every non-empty open set U, the measure of U is strictly positive. The second, if f is a continuous integrable function, is mu integrable and non-negative, and the integral of f is 0, then f is identical to 0. To prove part 1, we first of all observe that so suppose that mu of u is 0. Let's assume that it is 0. And observe now that every compact set can be covered by finite and many translates of u. For every compact set K in G, K is contained in the union of finite and many translates of U for some points x1 to xn, just by compactness and by the assumption that U is non-empty. Since the measure of mu is left invariant, so mu of U is 0, the measure of each of these sets is 0, so this implies that mu of K is 0. So the measure of every compact set is 0. This implies that mu vanishes on open sets by the property of inner regularity. Let's recall that the measure of every open set is the supremum of the measures of compact sets contained in this open set. This is just one of the axioms of for a double measuring. So mu vanishes on open sets, but by auto-regularity, the measure of an arbitrary Borel set is the infimum of the measures of open sets containing this Borel set. We get that mu is 0. Mu is 0 on all Borel sets by auto-regularity. And this is contradiction. The higher measure is assumed to be non-zero. This completes the proof of part 1. And part 2 readily follows from part 1. Well, indeed, if f is mu integrable and non-negative, and its integral is 0, then the standard measure theory implies that if f is 0 almost everywhere, with respect to the measure mu, that is, in other words, the measure of the following set of the preimage of positive numbers equals 0. But this set is open. This set is also open because f is assumed to be continuous. And we already know that the measure of a non-empty open set is strictly positive. So this is 0. This can be equal to 0 only if the set is empty. So by part 1, we deduce that f is 0 everywhere. And this completes the proof of lemma 1. Lemma 2. Again, we assume that G is a locally compact group. G is a locally compact group. And use an arbitrary random measure on G. Not necessarily left invariant. An arbitrary random measure. Let now f be a continuous compactly supported function on G, and define two functions g and h as follows. G of x is the integral with respect to mu of the right translate Rxf, and h of x is the integral of the left translate Lxf. I claim that the functions g and h are continuous. G and h are continuous. Well, I'll prove the continuity of G as the identity. The rest of the proof will be a simple exercise for you. Continuity of G at the identity. So we want to show that if X belongs to a sufficiently small neighborhood of the identity, this number is small. So this is, let's write this down explicitly. This is the integral of f of yx minus f of y d mu of y. We take now the absolute value here. This is dominated by the integral of the absolute value over G. So let's look at this expression. F was assumed to be continuous and compactly supported, and we know that every such function is uniformly continuous. So for every positive epsilon, we can find a neighborhood of the identity U such that f of yx minus f of x is less than epsilon for all x in G and for all y in U. Oh, sorry, for all y in G and for all x in U. F of y. Take f of y here. So for all y in G and for all x in U. So this is the uniform continuity of f. If the group were compact, this would be the end of the proof, because, well, this is less than epsilon everywhere, and the whole integral is less than epsilon times the measure of G. But G is not assumed to be compact, and the measure of G can be infinite in this case. So one more step is needed to deal with non-compact groups. Namely, we use the same trick as in the proof of the uniform continuity. So we'll let big F denote the support of little f. This is a compact set. We choose a relatively compact neighborhood of the identity. A relatively compact, symmetric neighborhood V of the identity. And let K denote the product of F and the closure of V. Since F and the closure of V are compact and the multiplication is continuous, we deduce that K is compact. And I claim that if Y is not in K, So I claim that actually we have to integrate over k only, because if y is not in k, then both numbers here are 0.
If x belongs to
you.
to v. Well, f of y is clearly 0, because if y is not in k, then y is not, moreover, y is not in f, is not in the support, and f of y is 0. And if f of yx is not 0, if f of yx is not 0, then yx is in the support, and this implies that y sits in f times x inverse. X belongs to v. X inverse also belongs to v because v is symmetric. This belongs to fv, and fv is contained in k. And this is a contradiction because y was assumed to be not in k. So we deduce that we have this equality, and as a result, we see that we can we actually integrate here over k only. G of x minus g of e is less than the integral over k f of y minus f of y, f of yx minus f of y. And now if x belongs to the intersection of v and u, then this is less than epsilon, and the whole integral is less than epsilon times the measure of k, which is finite because k is compact. Okay, so this implies the continuity of g at the identity. G is continuous at the identity. And now it's a rather simple exercise is to complete the proof.
So by using translates, we can reduce continuity at an arbitrary point to continuity at the identity. And for the left translates, the proof is essentially the same. Okay, we can now prove the uniqueness of the Haar measure. Theorem 2. Suppose that G is a locally compact group, and suppose that mu and nu are two left Haar measures. By default, Haar measure is a left Haar measure on G. Then there exists a positive constant C such that nu equals C mu. That is, the Haar measure is unique up to a multiplicative constant. To prove this result, we use the following trick. We take an arbitrary function, continuous compactly supported function f, which doesn't belong to the kernel of the functional I mu. That is such that the integral of f with respect to mu is non-zero. And we define a function df on G by the following formula. Df of x equals I nu of the right translate of f divided by the integral of f with respect to mu, which is assumed to be non-zero. Lemma 2 implies that this function is continuous. Df is continuous. I claim that this function doesn't depend on f. Before proving the claim, let's see how the claim implies our result. Let's denote this by star. Well, if we assume that star is true, if it doesn't depend on f, then we can substitute the identity here for x. And we see that I nu of f is equal to d of e. So d doesn't depend on f, so I denote it just by d. D of e times I mu of f. For every f which is not in the kernel of I mu. But now it's a simple exercise in linear algebra to show that if two linear functionals agree everywhere except a codimensional mod subspace, then they agree everywhere. This implies that actually they are the same everywhere. U equals d of e mu everywhere on the space of continuous compactly supported functions. And by looking at the respective measures, we deduce that mu equals c mu, where c is d of e. It is clearly positive because all measures, both measures mu and mu are positive. So now it suffices to prove the claim. Let's prove that this number doesn't depend on f. This is a little calculation based on Fubini's theorem. We take two functions f and g. Let me look at my notes. Yeah, we take two functions f and g, and the integral f, integrate f with respect to mu and g with respect to nu. I of f, I of g. So explicitly this can be written as the following double integral f of x, g of y, d mu of y, d mu of x. First we integrate g with respect to u, and we use the left invariance, of the measure nu. So by the left invariance of nu, this can be written as follows: f of x, g of x inverse nu, x inverse y, du of y, d mu of x. Here we use the assumption that nu is left invariant. Then we apply the Fubini theorem, and we interchange the integration signs. So now the first integral, which is inside, is taken with respect to mu. F of x, g of x inverse y, d mu of x, du of y. So now the first integral is taken with respect to mu, and now we use the assumption that mu is left invariant. So mu is left invariant, so we can change the variable x by the variable yx. And the integral will be the same. F of yx. So we replace x by yx, so we have x inverse, y inverse, and y. Y inverse and y cancel. So only x inverse survives. X inverse, yeah, that's correct. D mu of x, d mu of y. D mu of y.
And the final step we use Frobenius theorem once again. Again, we interchange the integral signs. Now the inner integral will be taken with respect to nu, f of yx, g of x inverse, g nu of y, g nu of x. So why is it convenient? So this is a right translate of f with respect to the right translate of f by x. So when we integrate this with respect to nu, we get the function, we get the following function, I u of Rxf. So we have to multiply this by g of x inverse and integrate with respect to mu. Okay, if we now divide both expressions by I mu of f, which is assumed to be non-zero, we see that the left-hand side will be I mu of g, while the right-hand side will be, so when we divide this by I mu of f, we get exactly this, df of x. df of x, g of x inverse, mu of x. Okay. Now we can easily show that this number doesn't depend on f. Indeed, let's choose two functions. Suppose we have two functions, f and f prime, are continuous compactly supported functions, and they don't belong to the kernel of I mu. So we can replace this here f by f prime. The left-hand side will be the same. So as a result, the difference, the integral of df minus df prime, well, g is an arbitrary, so we can replace g of x inverse by g of x, because g is arbitrary. So this integral is 0 for every continuous compactly supported function g. Let's now replace g by df minus df prime complex conjugate times g times the absolute value of g squared. This is also a continuous compactly supported function. Substitute it here, and we see that the following integral, df minus df prime, g squared is 0. But this is a non-negative continuous compactly supported function. Its integral is 0. Now lemma 1 implies that this function is identically 0. For every continuous compactly supported function g, and since this is true for every g, we deduce that df equals df prime. That is exactly the fact that df doesn't depend on f. Well, this is what we wanted to prove. And we have already observed that this property implies that our measures mu and nu are the same up to a multiplicative constant. And this completes the proof. So we see that the Haar measure is unique up to a constant. Okay, so that's all for today. At the next lecture, we discuss useful relation between the left and the right Haar measures. which is given by the so-called modular character. And then we begin discussing commutative Banach algebras, we define transform, and apply these concepts to constructing harmonic analysis on an arbitrary locally compact equation.